So the continuity equation, I don't think it needs its own name. It doesn't have to be called the continuity equation. It is just the conservation of energy. The continuity equation is just a special case of the conservation of energy relationship, where the conservation of energy is E in equals E out, or the change in energy equals nothing, or there's no change, right? The continuity equation says that the weight flow rate is constant across all sections. So we took the conservation of energy equation and we crossed out everything except for weight flow rate, which we usually call Q. So let's take a look at the situation that I'm talking about. I'm talking about a situation where there is fluid flowing in a pipe of diameter D1, and then the same amount of fluid goes through a pipe of diameter D2. So this is pipe of diameter D1, and I'm going to put up, we're going to look at the fluid as it goes between 1 and 2. So 0.1 and 0.2. At 0.1, the diameter was diameter 1, and at 0.2, the diameter is diameter 2, where D2 is less than D1. And we're looking at what's going to happen to that fluid when the diameter is less, and we still have to have the same fluid coming through. So here is our fluid, and our fluid is going to be moving at a velocity. And that velocity that it's going to be moving at here at position 1 is called V1. And it's going to be moving, of course, at a velocity at V2. And our question is, does it move at the same velocity? Does it move at a different velocity? Does the flow rate change? So let's take a look at what happened here is let's let some fluid flow in. We're going to let some fluid flow in, and we're going to let that fluid flow in at a flow rate Q1. So the fluid is flowing in at a flow rate Q, and then, or Q in, whatever we want to call it, we can call that Q in, and it's going to flow out at flow rate Q out. And the flow rate, this is volumetric flow rate. This is our volumetric flow rate, and it is measured in volume over time. But if we look at a volume, if we look at the volume here in this large diameter, and let's take that to a large extent, let's look at all of this volume. Let's look at a section of volume going through. There's this section, and then this section is going to be here. We actually don't need this little instantaneous volume. I'll just get rid of it. Now the section, this volume section is here, right? The section of volume went from here to here. Well, then it's going to go to here, right? But it has to be the same amount, because unless the fluid is incompressible. So it must take up the same amount of volume. But you see, area decreased. Therefore, this length, L, must have increased. And unless we could have compressed each little bit of this fluid, if we say if and only if the flow is incompressible, then volume at the volume in must equal volume out, because we simply can't take this volume of stuff and do anything other than move it through if these are moving at a velocity. We simply can't. It must flow out. The same amount of volume must flow out. And that's conservation of volume. That's called conservation of volume. So, therefore, if the fluid is incompressible, volume must be conserved. If the fluid is incompressible, volume must be conserved. If incompressible, therefore, volume in must equal volume out. But volumetric flow rate is volume over time. So for any unit of time, which means I can divide by time. I'm dividing both sides by the same amount of time. And if I divide both sides by the same amount of time, then I've said volume over time. So volume over time. Well, I just said over here, volume over time is flow rate. So then if the flow is incompressible, then Q in must equal Q out. The volumetric flow rate in equals the volumetric flow rate out. So what is the volumetric flow rate in? So we might remember this. We might remember volumetric flow rate, the definition of volumetric flow rate. Volumetric flow rate, Q, equals A times V. Why is volumetric flow rate Q equals AV? In meters cubed per second, usually, but it can have other units of volume and time. Why is it that? Because what we are looking at, Q equals its volume over time, and volume is area times distance. Here's the cross-sectional area. Area A times the distance that it traveled. Now this is my volume. So it is area, volume is area, times distance. Excuse me one moment. It is area times distance. That gives us volume over time. But then now I'm going to look at distance over time, and I'm going to remember that distance over time, but velocity equals distance over time. Yay, velocity also equals distance over time. Therefore, it just must be area times velocity. Q equals AV. That's our famous equation, Q equals AV for volumetric flow rate. So then how that relates to these two cross-sectional areas is we can observe then that Q in, which is A in V, velocity in, equals A out, V out, which is very, very handy. So that is a really handy relationship that as area changes, volume's going to change. So I like to always write it sort of, I'm always writing Q in is going to be A in V in equals A out, V out, because that's my Q out, which equals the Q in the first place. What a lot of people like to do is rearrange this. So I can see clearly that this is a relationship where if the area decreases, then the velocity is going to increase. And if this, in order to be the same as the other side, some people like to rearrange that and can see it visually better this way. This is just rearranging the equations. The second velocity over the first velocity is going to be a ratio of the, the first velocity over the second velocity is an inversely proportional to the ratio of the areas. And if you can relate area to diameter, then of course that would be area relates to diameter with pi, right? Um, and the pi's would cross out in the top and the bottom. So it would be d2 squared over d1 squared. And if we want to rewrite that, we can say it's d2 over d1 all squared. Now, some textbooks talk about this. I don't really. I always just remember Q equals AV in is going to be the same as Q equals AV out. And those relationships are going to be the same. So what does this mean? This means, so let's look at an example is like the tap. So everybody messes around with the tap when they're brushing their teeth when they're kids. So everybody, they turn on the tap. They're supposed to be brushing their teeth, but instead they put their thumb inside that tap, and you stick your thumb inside that tap, and what happens? The flow comes out really, really hard and really, really fast, and you can spray your brothers. So that's fun, but you couldn't do that if your thumb wasn't in the tap. So what were you doing with your thumb? You were changing the cross-sectional area to be smaller. You were minimizing the area out. But what happened with your tap is that your tap had to fit all of this volume. It had to fit all of this volume through this little space. But the flow rate in had to be the same as the flow rate out. So it did not get stronger. It did not get more pressure. It did not get a higher flow rate out. Felt like it did, but it did not get a higher flow rate. Conservation of energy says the flow rate stays the same. What happened? It got a higher velocity. So area out went down. Area out went down, but area out went down. So then velocity out had to go up, and you increase the speed, the distance over time, you increase the velocity that fluid came out. And this is just like a hose when you're, washing a car. You can turn the dial, and when you turn the dial, it gives you a higher cross-sectional area, just like over here. When you have a higher cross-sectional area, it's going to slow down your flow. It's velocity that changes, because it's velocity that changes with cross-sectional area. That's the relationship. So as you turn that dial, it increases that velocity. It slows down that, it increases that area. It slows down that velocity. It does not change the flow rate at all. And that's what's really important to remember in conservation of energy in fluid dynamics, is that flow rate is always conserved. Flow rate is always conserved. Therefore, when there is a change in shape, the velocity accounts for getting all of that flow throughout. So flow rate is always conserved. Q in equals Q out equals AV in equals A out V out, always.